Those close may notice these are the simulations I'm going to be talking about, a bunch of them. But let me start in a little more abstract way, which is imagine a world with millions of little computational elements which you could pour into a container, and they would organize themselves to form a brain, or at least learn like an animal does. That's been my goal in this project, and what I've developed is called the have and want schemata. So, like I said, some of it's operating there in minute detail. We present here today a set of pieces, each representing one bit of information and rules for adding new pieces when unknowns are detected and connecting them bidirectionally. Have and want represents a particular way to build controllers, and it's got some ups and downs to that. So I'll show you some of them operating in a Mac app I wrote, which is called Fractal Workbench, that generated all of these. And yes, there's an app for that. So I've been exploring these networks for the past 5 or 10 years, depending on how you count. And I found many little sweet spots, things that seem to work like, oh, hey, I'll take that. And the networks with interesting abilities. But I want to say 100 times there are a dozen more that I'm going to show you today at the website, which is down at the bottom, which you'll see, which is braingears.blogspot.com. So next I have a short trailer of the paper that I wrote. It's the abstract read, and it's got some images that I put up to kind of conjure what I'm talking about. So there's a kind of a bombardment of images and verbal, and see if you can pay attention to both. And again, if you don't get it all the first time, go back to the website.
The Have and Want Common Cortical Algorithm by P. Alan King. Abstract. Have and Want is a low-level cognitive schemata that processes bits of information bidirectionally. It is a common cortical algorithm whose tinker toy-like parts can construct networks that react powerfully in embedded environments. They exhibit many of the animal learning abilities described by Paget. Learning occurs when unknowns are detected, triggering the addition of new elements to the network. In this way, forward models can be built from experience, and many of these models can be linked together to form large, distributed, associative memories. Have and Want's level of abstraction lies well above neurological models, focusing on functionality and avoiding biological constraints. It also lies above computer and OR gates, which operate unidirectionally. In Have and Want, for every signal going one way, there is another signal coming back. Have and Want atoms continually reconcile the information on their links, each imposing a particular constraint. Its networks aggregate many single links to efficiently enforce large, sophisticated relationships. Have and Want operates below most AI architectures, which have algorithms that do not constrain bit-level computational locality. Although the examples given involve toy networks, we have a plan to extend the base algorithms by adding dynamically learned variables and noise tolerance to produce robust behavior.
So again, that's on the web. A lot of things are, actually there's a 30-minute read of the whole paper. I tried to prepare, and that's what came out, so it's a video. I think it gives you an idea of where we're headed, and what I have now is I'm going to attempt a live demo of the, off on the right there's like 6 or 8 networks. Umbrella is one where we talk about bidirectionality. Cat, dog, owl, I'll probably go into too, is where it learns a model of the world, simple model. And then there are various things that turn into motors and shaft encoders. So there's these little worlds where, gee, you can plug these things together and it does something that you need. Now, I'm going to argue that as you're able to build bigger and bigger assemblages of these, you're going to find some interesting stuff in there. That's what I'm in the middle of. So let me start. I'll start with Umbrella, and this is all magic. So this is a very simple Have and Want model. So down the bottom there's a vector, a bundle, I call it, of 3 bits. One is that it's raining, umbrella A and umbrella B. And up at the top, there's another bundle, which is the context I'm in. Right now, it's I want to stay dry. There could be many other things here. So what you can see, if it's raining, it comes up to this AND gate, which says, yeah, it's nice that it's raining, but I don't have. So the other thing is, if I have umbrella, then that goes up to, and it says I can stay dry. So that's the way you normally think of common forward reasoning. But if it's raining and you want to stay dry, it can, down the network, say, well, what am I missing here? Well, I'm missing umbrellas most here, so I want an umbrella. And which umbrella is closer? Well, umbrella A is closer, so I want umbrella A. But now if I do a funny thing which says, for instance, umbrella B is closer, then what happens, so if umbrella B... So anyhow, I was just going to repeat that, and that's probably not worth repeating. This is the various scenes that I can build with Fractal Workbench, and I'm just bringing it up again and seeing if it's happier. So in Fractal Workbench, I'll pick another scene, which is a simulator. So these basically, cat, dog, owl, has a bundle of the world that has like 8 bits in it, which are labeled as labeled here. We've got a cat. So if I put the first sample in, you notice that there's owl and hiss, but there's no model. So it goes over here to this right head, and the right head says, we better make a new element for this. This is something new. So it makes the element, puts it in the thing, and now the model recognizes owl and hiss, and there are no errors that go to the right head. So the right head kind of clears itself out. So we could do another one. Suppose we add one piece to it, so that's owl, screech, and hiss. There's only one error, and that goes to make a single thing up in the top. So you can see that if you're presented with a bunch of models you can build, and now all of these things are memorized, and it can go to more. Again, all of these are explained probably much better than I have them on the web. Let me go to the final, okay. So this is another one, rather than a model that was built, this is a tree, and what's coming in is dotted on the, basically all the letters are presented serially with a separator character, and it builds a tree. Now this tree is interesting because once you finish generating it, you can hit one of the top leaves, and it goes dotted out the bottom. So it's bidirectional with the sequentiality, which is a very interesting property. So that's it about trees. Up to this point, we've been dealing with small systems, but I want to talk about where I see us going in big systems. This is the philosophy of HaveNWant. You can take a quick read of it. 1-bit bidirectional, start small. Don't worry about combinational explosions. Toy networks, fine networks, do fixed networks first, and record everything possible. So these are the kind of things that guide me in where I'm going, and where I'm going is this picture. This on the left is a brain. On the right is the HaveNWant architecture I'm talking about. The green is the motor sensor areas. So in the cortex, there's two lobes. The thalamus and basal ganglia go into predominantly motor cortex, and then we do all the things in here. We have all the models we've been talking about. I have a lot to work on given what I'm hearing in this conference. But ultimately, the top part of the world has to do with coincidence. And ideally, you'd like to have a cell for grandmother. You'd like to have a cell for every single event that you've seen. Now, of course, there's equivalences. There's a lot of things that make that complicated. But in a simplistic view, if you had one cell here, which represents the conference today, then if you tickled that cell, it would come down into the world model and set up the world model, which is appropriate for where we are right now in this room. So that's, and of course, that world model talks to the world through the I/O sensors, which come out the bottom. But there's one more path that I'm exploring, which basically it's an attentional learner. There's a thing I call the Maslow. Maslow basically said that the most important things get done first. You know, if someone's stepping on my toe, I don't really care about the martini I had last night. I care, you know. So there's this multiplexer which takes the most important of the world models and allows you to kind of, it's shown a little better here. This is the hippocampus and entorhinal cortex, which is the gateway to it. I don't know how it works. One of the things I think it does, though, is repeats patterns over and over, because learning in this area involves axon, I believe involves axon growths. And if you repeat the same patterns over and over again. So this is the big picture, and I think that's the whole presentation. I will take questions. Well, how do people see this with respect to the work they're doing? And let me plant a seed answer is that some of the stuff that I see each of you doing might be in the various areas, like the coincidence detection, and so you have almost an answer coming. Yes.
No, I was just wondering. So, trying to figure out what are the current limitations of your architect. What things it cannot do yet?
Well, I have not worried about context, and context is where Q-learning lives. I know that each of these actors that you saw is also going to have a Q-learning system that drives it particularly to its desired state. I haven't done that yet. The whole notion, I'm dealing in toy environments without noise. There's a lot of stuff there that hasn't been done. The other thing is the strategy that I have for kind of recording everything and figuring it out later. Well, it's not later yet. I have to, there's a ripe area to explore there. I need about 5 PhD students.
Did you say that Q-learning is related to the context? Or did I
Yeah, I think the plan I hope to carry forward with HaveNWant is every actor has an evidence bundle of the way the world is, and a context bundle of the way its superiors want the world to be, have and want. Okay, and so one of these might be I am standing. So when I push on the want for I am standing, I would like this to happen. But for that to happen, it might be I have to take the recorder off. I have to do a bunch of things before. I think I've answered your question. Am I close?
more like an episodic description that you are after?
Okay, yes. Higher level things look like episodes to lower level things. There's a way of doing dynamic linking so that you can start to put in the constraints of lower than or higher than that we talked about in other things. Okay, I'm done. Let's thank our speaker.